there are stellar endings that arrive like a slow resignation, a star easing down its brightness over millions of years, lowering the lights one steady notch at a time. And there are endings that arrive like a sudden signature on the sky, too bright to ignore, too brief to be ordinary, a kind of cosmic punctuation that turns a quiet sentence into an exclamation point. A supernova is neither a simple fade nor a simple flash, really. It is not just a star blows up, and it is not one single thing wearing one dramatic name. It is a family of events with different engines, different evidence trails, and different reasons for why the light rises, why it lingers, and why it falls away again. Some supernovae are the final collapse of a massive star's core, when gravity finally collects what pressure can no longer hold. Others are thermonuclear runaways on the surface or within the compact hush of a white dwarf, when conditions become just right for a flame to race through degenerate matter. The same word covers both, the same headline, two different physics stories. And tonight, we will follow the evidence gently, one calm detail at a time. Back in my office, the air feels layered, as if the room has been built out of shells. There is the outer layer, the quiet perimeter, bookshelves, a coat hung neatly on a hook, the soft boundary of walls holding in warmth. There is a middle layer, my desk, the lamp, the place where notes accumulate and patterns begin to show. And there is an inner layer, the small core of attention, a folder set squarely beneath the lamp's circle of light, labelled in careful handwriting, Supernovae. The lamp itself hums faintly, steady and contained, like a star that has learned how to shine for a long time without changing its mind. The window beside me is a dark pane of sky, a reminder that most of the universe spends its time in silence. On the desk, a mug sends up a thin ribbon of steam that curls, thins, and disappears, like expanding gas cooling as it travels, like brightness that must fade because it is doing work on the space around it. A drawer sits half open, full of paper clips and spare pens, and it makes me think of a star's interior, compartments of different materials, arranged not by tidiness, but by density, by what sinks and what floats, by what can fuse and what cannot. My name is Madeline Rowe, and tonight this is the science of supernovae for sleep. I like to begin any case with the simplest, most faithful witness. Not the gossip of speculation, not the glamour of an artist's impression, but the plain record of what arrived at our instruments. For supernovae, the most faithful witness is light as a function of time, a curve, a trace, a line that rises and falls. Astronomers call it a light curve, and it is exactly what it sounds like. The brightness of an object plotted over days and weeks and months, sometimes longer, like a heartbeat seen from far away. In that curve, a supernova tells you how quickly it was lit, how long it stayed, and how it cooled into invisibility. If you listen to nothing else tonight, you can listen to that shape alone. Imagine the graph paper as calm as a shoreline. Time runs from left to right, like a slow walk. Brightness rises upward, like a tide coming in. A supernova's light curve is the tide line of an explosion. Some rise quickly, sharp as a steep beach. Some rise more gradually, like a wide shelf under shallow water. Some pause on a plateau, as if the tide arrives and then holds itself in place for a while. Some decline in a smooth slope. Some break into a steeper fall, then a gentler tail. The shape is not decoration, it is the physics leaving footprints. One reason the shape matters is that it can be compared across distances. The same event viewed from different galaxies will look fainter if it is farther away. But the way it changes with time, the rhythm of rise and fall, remains. And when many supernovae are gathered together, their light curves begin to sort themselves into families. Some family members look remarkably consistent, as if they share a common blueprint. Others vary widely, as if the same ending can be reached by many different paths. This is where the case file splits into two main tabs. On one tab, thermonuclear supernovae, often called type 1A. On the other, core collapse supernovae, the endings of massive stars, often sorted into types 2, 1b, and 1c. Those labels are observational, not moral. They are not awards. They are simply a way to say, in the spectrum we saw hydrogen, or in the spectrum we did not. The spectrum is the second faithful witness, light separated into its colours, with lines and gaps that act like signatures of elements. Light curves tell us how brightness evolves. Spectra tell us what the matter is doing and what it contains, and how fast it is moving. I keep the classification gentle by turning it into a question you can hold in one hand. When a supernova's light is spread out, do you see hydrogen? If yes, we tend to call it type 2. If no, we tend to call it type 1. Then, within those broad categories, there are subfamilies, some with silicon features, some with helium, some with narrow emission lines shaped by interaction with dense surrounding gas, some with plateaus, some without. The taxonomy can be a forest, and you do not have to walk every path tonight. We can stay on a calm trail, hydrogen present or absent, and then what that implies about the star's outer layers at the moment the explosion began. Hydrogen, in this sense, is not just an element, it is a clue about the envelope. A massive star may keep a thick hydrogen-rich outer layer until the end, or it may lose much of it through stellar winds or binary interaction. If the hydrogen is present in the spectrum, it suggests that envelope is still there, and it will shape the light curve by trapping radiation and holding heat in, like a thick coat. If the hydrogen is absent, the explosion is happening in a star that has been stripped, showing deeper layers, helium, carbon, oxygen, closer to the surface. The coat is gone, and the light can change faster. Now, for type 1a, hydrogen is generally not seen either, but for a different reason. The star involved is not a massive hydrogen-rich star at all. It is a white dwarf, compact and dense, the leftover core of a star like the Sun. In a binary system, it can gain matter from a companion. Under certain conditions, that gained mass and pressure can lead to a thermonuclear runaway. The result is an explosion powered by nuclear burning, with its own characteristic spectral features and its own light curve regularities. So the first calm fact is this: the universe has at least two major ways to write supernova across a sky. One is collapse, one is runaway burning. The next, calm fact, is that we can tell which we are looking at, not by intuition, but by the evidence. Hydrogen lines or not, silicon features or not, plateau or not, and the deeper rhythm of the light curve. Let's open the core collapse tab first, because it begins with something almost tender in its inevitability. A massive star trying for millions of years to keep gravity at bay. A star is a negotiation between inward pull and outward pressure. Gravity wants everything closer. Pressure, largely produced by heat from nuclear fusion, pushes back. For most of a star's life, this negotiation is stable enough to feel like peace. Hydrogen fuses into helium. Helium can fuse into carbon and oxygen. In the most massive stars, fusion continues into heavier elements, building an onion-like interior, shells of different fuels burning at different temperatures, layered by density. The further inward you go, the hotter and denser it becomes. The more advanced the fuel, the faster it burns. There is a quiet tragedy in that acceleration. Hydrogen burning can last a very long time. Later stages can be much briefer. Silicon burning can happen on timescales that are almost shocking compared to a star's lifetime. It is as if the star spends eons learning to breathe, then suddenly runs through the last pages of its book in a single night. And then it reaches iron. Iron is where fusion stops being a source of energy. For lighter elements, fusing them can release energy and support the star. For iron and beyond, fusing them requires energy. It is a ledger that goes the wrong way. The core becomes iron-rich, dense, and unable to generate the same outward pressure through fusion. The star can keep going for a moment by other means: thermal pressure, degeneracy pressure in some contexts. But the core is no longer being buoyed by a steady furnace of fusion. Gravity has been patient. Gravity does not get bored. Gravity continues. At a certain point, the core can no longer support itself. Collapse begins. And here it is important to keep the language accurate without making it harsh. Collapse is not a leisurely settling. It is rapid. In the center, matter falls inward at a significant fraction of the speed of light. Electrons are squeezed into protons, producing neutrons and neutrinos. The core stiffens as it becomes neutron-rich. In many models, the inner core rebounds slightly, like a compressed spring returning some energy, sending a shock wave outward. But that shock does not have an easy job. It plows into infalling material. It loses energy. The explosion is not guaranteed by a simple bounce alone. Something else must help. That something else is one of the most fascinating, quietly dominant facts of core collapse supernovae, neutrinos. The core becomes so dense that neutrinos, normally ghost-like, begin to interact. A vast amount of gravitational binding energy is released as the core forms a neutron star. Most of that energy escapes as neutrinos over a short burst. The optical light we see, the bright star in the sky, is only a thin receipt compared to the neutrino budget. Yet a small fraction of that neutrino energy, deposited in the right place behind the stalled shock, can help revive it, pushing the shock outward again and allowing the star's outer layers to be expelled. This is a story where the smallest, most elusive particles can influence the largest, most visible fireworks, if the geometry and timing are right. We know neutrinos matter because the universe once gave us a rare confirmation in our own neighborhood. In 1987, a supernova exploded in the Large Magellanic Cloud, a companion galaxy to the Milky Way. Detectors on Earth caught a handful of neutrinos arriving in a brief burst. It was not many. It did not need to be. The mere fact they were seen, in time with a supernova, supported the idea that core collapse produces a neutrino flood. It was a whisper from the core, detected across intergalactic space. The light arrived too, and astronomers watched the event's brightness change with time, tying particle physics and astrophysics together with one celestial event. It is the kind of evidence that makes a case feel real, not just theory, but a few counted particles, a timestamp, a correlation. Now, what does a core collapse supernova look like in the light curve? It depends on the envelope. If the star retains a thick hydrogen envelope, the light curve can show a plateau. The brightness rises, then holds relatively steady for weeks. This plateau is not a pause because nothing is happening. It is a pause because the physics is regulating how energy leaks out. The ejected hydrogen-rich envelope expands and cools. Hydrogen recombines, electrons reattach to protons, which changes the opacity, allowing radiation to escape in a controlled way. The envelope is like a thermostat and a curtain at once. As it expands, the temperature and transparency evolve together, producing a long, relatively flat stretch in brightness. In other core collapse events, the envelope is thinner or structured differently. The light curve may decline more steadily without a long plateau. In some, interaction with dense circumstellar material can produce narrow emission lines and prolonged brightness as shocks heat surrounding gas. These are cases where the star did not go quietly into collapse. It was shedding matter in the years or decades before the end, leaving a dense environment for the explosion to run into. The light curve becomes a record not just of the explosion, but of the star's final years of mass loss. And then there are stripped envelope supernovae, types IB and IC, where the outer hydrogen has been mostly removed, and in IC, the helium can be weak or absent as well. These explosions can show faster evolution in their light curves because there is less envelope to trap radiation. The spectrum reveals deeper layers. The overall diversity among core collapse events is large. The light curves vary because progenitors vary. Mass, metallicity, rotation, binary stripping, circumstellar environments, and explosion energies all contribute to a broad gallery of outcomes. In my office, I picture this diversity as different ways the room could be arranged before a single event. A different set of objects on the desk, a different thickness of paper in the folder, a different density of notes pinned to the corkboard. The same lamp could be shining, but the way the light fills the room would differ depending on what is in the way. In stars, the furniture is the envelope, the shells, the composition, the density gradient. The explosion is one motion. The light we see is how that motion interacts with the structure. Now let's open the thermonuclear tab, the Type 1A story, because it offers a different kind of calm, regularity. Not perfect, not without complications, but surprisingly consistent compared to the sprawling variety of core collapse. Type 1, as supernovae have played a special role in astronomy because their light curves and peak brightnesses can be standardized. They are bright enough to be seen across enormous distances, and similar enough that, with careful corrections, they can be used as distance indicators. They helped reveal that the expansion of the universe is accelerating, one of the great discoveries of modern cosmology. But we do not need to rush there tonight. We can stay close to the mechanism and the evidence. A white dwarf is the leftover core of a star that has stopped fusion and shed its outer layers. It is roughly Earth-sized, but contains a mass comparable to the Sun's. It is supported not by heat, but by electron degeneracy pressure, a quantum mechanical effect arising because electrons cannot all occupy the same quantum states. This form of support does not depend strongly on temperature, which makes it peculiar. A white dwarf can be cold and still support itself, but it also means that adding mass can push the dwarf toward a limit, a threshold where support fails. In many Type 1A scenarios, a white dwarf in a binary system gains matter from a companion. As it approaches a critical mass, conditions in its interior can become ripe for carbon fusion to ignite. And when fusion ignites in degenerate matter, it can run away. In ordinary stars, if fusion increases, the temperature rises, pressure rises, and the star expands a bit, cooling itself and regulating the burn. In a degenerate core, pressure does not respond the same way to temperature. The thermostat is broken. A small ignition can become a flame that spreads, accelerating, converting carbon and oxygen into heavier elements, releasing energy rapidly. The white dwarf can be unbound. In the simplest picture, it is disrupted entirely. The explosion synthesizes large amounts of intermediate mass elements and ion group elements, including radioactive nickel-56. That nickel matters because it is one of the quietest, steadiest power sources for the light curve's decline. After the explosion, the ejector expands. Without ongoing power, it would cool and fade quickly. But nickel-56 decays to cobalt-56, which decays to iron-56, releasing gamma rays and positrons. Those decay products deposit energy into the expanding material, heating it and producing light over weeks and months. The early brightness is influenced by the explosion energy and the opacity of the ejector, but the late-time tail, especially in many supernovae, is linked to radioactive decay. This is not a metaphor, it is a measurable chain: half-lives, energy deposition, brightness decline. A supernova, in this sense, is partly a glowing cloud of freshly made isotopes, cooling as it expands while being gently reheated from within by nuclear decay. If you want a single restful image that captures this, imagine the steam from the mug on my desk. It rises because it is warm. It thins because it mixes with cooler air. It would vanish quickly if the mug were cold. But if the mug continues to supply heat, the steam persists longer, even as it disperses. In a supernova, expansion is the dispersal. Radioactive decay is the persistent heat. The balance between the two shapes the fading light. Type 1. A light curves have an additional property that makes them particularly useful: a correlation between how bright they get and how quickly they fade. Brighter. Type 1. A supernovae tend to decline more slowly. Dimmer ones decline more rapidly. This relationship, refined through observational work, allows astronomers to standardize them. You observe the light curve shape, infer how intrinsically bright it was likely to be, and then compare to how bright it appears to estimate distance. It is not magic. It is careful statistics and calibration, and it depends on understanding and controlling systematic uncertainties. But the core idea is gentle. The shape of the light curve carries information about the explosion's intrinsic scale. Not every Type 1a is identical. There are peculiar events, subluminous ones, overluminous ones, and ongoing debates about progenitor channels, single degenerate scenarios with a non-degenerate companion donating mass, double degenerate scenarios with two white dwarfs merging, and other variations. Some models involve a deflagration to detonation transition, where a subsonic flame transitions into a supersonic detonation under certain conditions. The details of flame propagation, how turbulence wrinkles the flame, how burning proceeds in 3 dimensions, remain challenging. But tonight, we can hold the high-level picture. A compact star supported by quantum pressure pushed toward ignition, then consumed by runaway fusion, producing a characteristic spectrum and a light curve shaped in part by nickel decay. Now let's return to the evidence cabinet, because a case grows stronger when different kinds of observations converge. Light curves are one cabinet, spectra are another. A third is the remnant, the physical debris left behind, visible long after the bright flash has faded. Remnants are slow motion stories. They show us where matter went, what it contains, and how the explosion interacted with the surroundings. If a supernova is the moment a file is stamped and sealed, a remnant is the reopened archive decades or centuries later, when you can lay out the fragments and see what kind of structure was thrown into space. One remnant in particular makes a compelling exhibit because it is both beautiful and informative. Cassiopeia A. It is the debris of a supernova in our galaxy, relatively young on astronomical timescales, roughly a few centuries. It is bright in X-rays and NASA's Chandra X-ray Observatory has mapped its structure in remarkable detail. Chandra's data allows astronomers to identify different elements in the remnant and to infer their distribution and velocities. It is like a chemical map of an explosion, drawn not in ink, but in photons. In this remnant, astronomers have argued for evidence of something that happened in the hours before the star collapsed. The phrase inner conflict is poetic, but the idea is physical. Layers in the star's interior may have mixed, with a silicon-rich layer pushing outward and breaking into a neon-rich layer shortly before the end. In a massive star, layers are not simply static shells like a tidy onion. They are dynamic, with convection, turbulence, burning fronts, waves, and instabilities. The last stages of nuclear burning can be chaotic. If the interior rearranges itself shortly before collapse, it could seed asymmetries in the explosion, influencing how the shock propagates and how the ejector is distributed. This is not a story of a perfectly spherical blast. Real supernovae can be lopsided. Jets, plumes, and clumps appear in observations. Neutron stars can receive kicks, moving at high speeds, as if the explosion was not perfectly balanced. Cassiopeia A is a reminder that the last hours of a star's life can matter, not in a mystical way, in the practical way of fluid dynamics. If the interior is already in motion, the collapse and explosion inherit that motion. In my office, I can feel this as an atmosphere rather than a spectacle. The room is quiet, but not perfectly still. Air circulates, heat rises near the lamp and drifts towards the cooler window. Somewhere in the building, a ventilation fan cycles on and off, shifting pressure slightly, like a slow wave. A supernova progenitor can be like that in its last hours, a structure that is nominally stable, yet full of subtle flows. And then, when the core collapses, those flows become part of the record. If we zoom out from a single remnant to the broader sky, the modern era of supernova science is defined by another kind of evidence: surveys. Not one telescope staring at one object, but wide fields of view, repeated observations, time-domain astronomy that turns the sky into a movie. The logic is simple and powerful. If you want to catch transient events, things that appear and fade, you return to the same patch of sky again and again. You build a baseline. You look for changes. You trigger follow-up. You compile catalogues. NASA's Nancy Grace Roman Space Telescope is designed to play a major role in this survey era. One of its planned wide-field surveys aims to repeatedly observe the same region of sky on a steady cadence, finding and tracking a vast number of cosmic explosions. The promise is not just a handful of beautiful events. It is statistics. It is thousands upon thousands of light curves measured in a uniform way. It is the ability to compare supernovae across cosmic time with consistent instrumentation and careful calibration. When a survey is executed well, it does something soothing for science. It reduces the chaos of selection. It makes the sample more complete. It helps us see patterns that would otherwise be hidden by bias. Bias matters because the sky does not present itself evenly. Bright things are easier to notice. Nearby things are easier to study. Events near the bright centers of galaxies can be missed. Dust can hide explosions. Weather on Earth interrupts schedules. Instruments have sensitivities and limits. A survey with a planned cadence and a stable platform can fill in gaps and provide a cleaner dataset, though never perfect. Roman, observing from space with a wide field and infrared sensitivity, is intended to find many more events than traditional pointed observations could. It is like moving from occasional witness statements to a full surveillance camera archive, still requiring interpretation, still requiring calibration, but rich with consistent detail. This brings us to another quietly important corner of the case file: catalogues. A catalogue is not glamorous. It is a ledger, a table, a set of entries with coordinates, dates, classifications, host galaxies, redshifts, and references. But catalogues are the scaffolding of supernova science. They allow populations to be studied, how often different types occur, how they correlate with galaxy properties, how discovery rates change with time, how classification schemes evolve. Catalogues also reveal the messy human side of astronomy: inconsistent naming conventions, repeated entries, uncertain classifications, distances revised after new measurements, coordinates improved with better astrometry. Efforts to unify and clean catalogues are an act of care. They turn a chaotic history of discoveries into a dataset that can be trusted for statistical inference. If my office is a metaphor for supernovae, then the file cabinet is a metaphor for catalogues. Each drawer is a year. Each folder is an event. Some folders are thick, with spectra, light curves, and follow-up papers. Some are thin, with a single report and an uncertain type. Some have a sticky note that says, "Coordinate corrected," or "Classification disputed," or "Host galaxy distance updated." The cabinet is not exciting, but it is where the case becomes more than anecdote. And speaking of anecdote, there is another kind of record that predates modern catalogues by centuries: historical observations. Long before CCDs and spectra, humans looked at the sky with their eyes and noticed when a new star appeared where none had been. These guest stars, recorded in Chinese, Korean, Japanese, Arabic, and European sources, are part of astronomy's shared memory. They are not just romantic stories, they are data points. They tell us when a bright transient appeared, how long it remained visible, sometimes where it was seen relative to known stars. When we can connect a historical guest star to a modern remnant, like the Crab Nebula to the supernova of 1054, we gain a timeline, an explosion date, a remnant age, a chance to test models of expansion and energy. SN 1006 is one of the brightest supernovae recorded, visible in daylight according to some accounts. The supernova of 1054 left the Crab Nebula, a pulsar-powered remnant that remains a laboratory for high-energy astrophysics. Tycho's supernova of 1572 and Kepler's of 1604 were crucial in shifting scientific thinking, showing that the heavens could change. Each of these events, when linked to modern observations, becomes a bridge between eras, from naked eye astonishment to X-ray spectroscopy. But we can keep this bridge gentle. We do not need to dramatize it. We can treat it as continuity. The sky changes. Sometimes the changes are subtle and slow. Sometimes they are sudden and bright. Humans noticed, instruments refined. The evidence became more precise. Yet the core act, watching the sky for changes, remains the same. Now, let's return to the center of the file. What actually powers the light we see? Because explosion is a word that can hide more than it reveals. For both core collapse and thermonuclear supernovae, the optical light is not simply the initial burst of mechanical energy. It is radiation diffusing out through expanding material. It is heat deposited and reprocessed. It is opacity changing as ions recombine. It is radioactive decay heating the ejector. It is, in some cases, shocks ploughing into surrounding gas and converting kinetic energy into light. In the earliest moments after a core collapse supernova, there can be a shock breakout. The shock wave reaches the surface of the star and a burst of radiation escapes. This can be brief and difficult to catch, especially for large, distant stars. but it is a real physical stage. After that, the expanding envelope radiates. In type 2 P supernovae, the plateau phase is tied to hydrogen recombination in the envelope. After the plateau, as the envelope becomes more transparent and the photosphere recedes, the light curve often transitions to a radioactive tail, influenced by the decay of nickel and cobalt. In stripped envelope supernovae, the absence of a thick hydrogen envelope changes the diffusion time, often leading to a faster rise and decline, with the light curve more directly reflecting radioactive heating and the lower mass of ejecta. In type 1a supernovae, the light curve is closely tied to the amount and distribution of nickel synthesized. More nickel generally means a brighter peak and a slower decline, because there is more heating to counteract expansion, cooling. The details depend on opacity and the mixing of elements, but the broad relationship holds. This is why the light curve can act as a diagnostic. It is a calorimeter of sorts, telling us how much radioactive fuel was made. If you want to rest in one of the simplest quantitative ideas in astronomy, you can rest in the notion of magnitudes. Brightness in astronomy is often measured on a logarithmic scale. A difference of 1 magnitude corresponds to a specific factor in brightness. It is a scale built for the eye and for the immense dynamic range of the sky. It means that small numerical differences can represent large physical changes. A supernova can outshine its host galaxy for a brief time, and then fade below detectability. The magnitude scale makes that vast change manageable to write down and compare. But we do not need to calculate anything tonight. We can let the scale be a quiet reminder. The universe often works in ranges that feel too large, and humans build tools, scales, graphs, catalogues, to hold those ranges gently. Now, there is another layer of evidence that is both intimate and grand: the elements themselves. Supernovae are not only endings, they are factories and distributors. Many of the elements heavier than helium are synthesized in stars and in stellar explosions. Massive stars build up elements in their cores through fusion up to iron. Supernova explosions, through explosive nucleosynthesis and neutron-rich environments, can create and disperse a variety of elements. The details of where the heaviest elements are made, especially those produced by rapid neutron capture, the R process, are an active area of research, with neutron star mergers now known to contribute significantly, but core collapse supernovae and other explosive events still play roles in the chemical evolution of galaxies. At a minimum, supernovae enrich the interstellar medium with oxygen, silicon, iron, and many other elements. They seed future generations of stars and planets. If you hold a coin in your hand, you are holding metal forged in stellar interiors and dispersed by ancient explosions. If you breathe, you are using oxygen produced in stars. This is often stated in a dramatic way. We are stardust, but it can be said quietly too. It is a material continuity. The universe recycles. Supernovae are one of the recycling mechanisms, energetic enough to lift heavy elements out into space and stir them into the galactic medium. Now, let's look again at the question of diversity, because the taxonomy of supernovae has grown more complex over the decades. As instruments improved and surveys found more events, astronomers encountered objects that did not fit neatly into old categories. Transitional events appeared. Peculiar subtypes were proposed. Some supernovae showed properties between types 2 and IB, or between normal type 1A and other thermonuclear variants. Some showed signs of interaction with circumstellar material. Some were unusually luminous, challenging standard power source explanations. The classification system is not static. It evolves because the sky keeps offering new variations, and because the boundaries between categories are sometimes the boundaries of our observational sampling rather than sharp divisions in nature. This is normal for science. A classification is a map. As you explore more territory, the map gains detail. Rivers that were once drawn as a single line become braided streams. Mountains that were once a lump become distinct peaks. The supernova map has become more detailed and sometimes more confusing, but the underlying strategy remains calm. Classify by observable features, then link those features to physical mechanisms, then refine the categories as understanding improves. To keep the map restful, we can focus on a few anchor points. Anchor 1, hydrogen present versus absent, which tells us about the envelope. Anchor 2, silicon features characteristic of many type 1 A supernovae. Anchor 3, the plateau in type 2 P light curves. Anchor 4, the radioactive tail. Anchor 5, interaction signatures like narrow lines. With those anchors, you can drift through the broader taxonomy without needing to memorize every subclass name. Now let's return to the core collapse mechanism for a moment, because there is a subtle but important concept there. The explosion is not simply the release of stored thermal energy. It is, in a sense, an energy conversion problem. Gravitational potential energy becomes kinetic energy of infall, becomes thermal and neutrino emission in the dense core, becomes, through complex processes, kinetic energy of an outgoing shock and the ejection of outer layers. The optical light is a small fraction of the total energy budget, shaped by how energy is deposited and diffuses out. This is why a supernova can be both unimaginably energetic and yet visible as a light that fades within months. The mechanical energy goes into accelerating matter. The matter becomes a remnant, expanding and interacting with the interstellar medium for thousands of years. The light is a temporary tracer, like a glow on a moving object that tells you where it is in the dark, but does not represent the full energy it carries. In Cassiopeia A, we see the result: a shell of debris expanding, shock fronts glowing in X-rays, knots of enriched material, and a compact object left behind, a neutron star. That compact remnant is another piece of evidence. Core collapse supernovae often leave behind neutron stars or black holes. Thermonuclear type 1. A supernovae, in their simplest form, do not leave a compact remnant because the white dwarf is disrupted. So the presence or absence of a remnant, when it can be detected, is another clue to the underlying engine. Neutron stars themselves can be quiet in one way and extreme in another. Tiny, dense, rapidly rotating, magnetized. In some remnants, pulsars energize surrounding nebulae, like the Crab. In others, the remnant may be more subtle. But the principle holds. Collapse can leave a core behind, and the core can become a long-term source of energy for the remnant's evolution. Now, as the night goes on, I like to imagine the office itself as a light curve. In the beginning, the lamp is steady, representing a star's long main sequence life. Stable burning, stable light. Then, as the case progresses, the room's lighting changes. Not literally, not in a way that startles, but as an internal metaphor. There is a phase where the desk becomes crowded with papers and notes, representing late-stage burning shells, faster processes stacked closer together. The air feels warmer near the lamp, like energy production concentrated in deeper layers. Then there is a moment of transition. A drawer closes softly with a click, like a threshold crossed. And then, in the imagination, a brief brightening, just a little increase in the lamp's glow, like the rise of a light curve, a peak, and a slow return to baseline as the room settles into a quieter, cooler state again. This metaphor is not meant to be cute. It is meant to help you feel the structure of the physics without needing equations. A star's life is long and layered. Its ending is rapid and decisive. The observable evidence, the light curve, rises and falls in a patterned way that can be mapped onto a calm interior narrative. Now, let's take a slow walk through the stages of a light curve as if it were a corridor in a building. The first stage is the rise, brightness increasing as radiation begins to escape. In many supernovae, the rise time is tied to diffusion. Photons created by shock heating or radioactive decay do not escape instantly. They scatter through the expanding ejecta. The denser the ejecta and the higher the opacity, the longer the diffusion time and the slower the rise. The mass of ejecta, the energy, and the opacity all matter. In type 1, a supernovae, rise times are typically on the order of a couple of weeks, though details vary. In core collapse supernovae, rise times can vary more widely, depending on progenitor radius and envelope properties. Then comes the peak, the time when energy deposition and radiation escape balance in such a way that brightness reaches a maximum. Peak brightness is not simply how energetic the explosion was. It is, in many cases, strongly influenced by how much radioactive nickel was produced and how effectively its decay energy is trapped and thermalized. In core collapse events, shock-deposited energy and recombination can also shape the peak and plateau. After peak, the decline begins. As the ejecta expands, it becomes more transparent. Energy escapes more easily. If radioactive heating is strong enough and trapping remains significant, the decline can be slower. If heating is lower or trapping decreases, the decline can be faster. In type 2 P supernovae, the plateau is a special kind of decline. Brightness remains roughly steady because recombination regulates the photospheric temperature and opacity. And then there is the late time tail, the slow fade, often roughly following the decay rates of cobalt to iron when gamma-ray trapping is efficient, and then deviating as trapping decreases. At late times, the ejecta can become thin enough that gamma rays escape without depositing their energy, steepening the decline. Observations of late-time light curves can therefore constrain ejecta mass and density structure. It is all in the fade. The fade is not an afterthought, it is the event continuing in slow motion. If you want to picture late-time trapping, think of the office window as a boundary. Early in the evening, the blinds are mostly closed, and light from the lamp stays within the room, bouncing off walls and papers. Later, the blinds open slightly, and the same light can leak out. In a supernova, early on, the ejecta is thick, and photons are trapped. Later, the ejecta thins, and energy escapes more readily. Now, there is a temptation in supernova storytelling to focus on the extremes, the violence, the shock, the scale. But the science becomes calmer when you focus on constraints. A light curve is a constraint. A spectrum is a constraint. A remnant map is a constraint. A neutrino detection is a constraint. Each piece limits what could have happened and supports what likely did happen. In that sense, supernova science is a discipline of narrowing. Many mechanisms might be imagined, but only some fit the observed evidence. This narrowing becomes even more powerful when you have many events, which is why surveys like Romans are so valuable. When you have thousands of light curves, you can find the common shapes and the outliers. You can characterize distributions, typical rise times, typical peak brightnesses, correlations with host galaxy type, trends with redshift. You can identify rare classes that might be missed in small samples. You can test whether type 1a standardization holds across cosmic time, or whether subtle evolution in progenitor properties introduces systematic shifts. You can search for early bumps in light curves that might indicate companion interaction in some progenitor channels. You can watch the sky with enough patience and repetition that transient events become a statistical population rather than a collection of anecdotes. Outliers deserve their own quiet shelf in the file cabinet. Some supernovae are far more luminous than typical events. These superluminous supernovae may be powered by different mechanisms: interaction with dense circumstellar material, central engines like magnetars injecting energy, or in some cases pair instability processes in very massive stars. Pair instability supernovae are a particular theoretical class where, in extremely massive stars, high-energy photons in the core can produce electron-positron pairs, reducing radiation pressure and triggering contraction and explosive oxygen burning, potentially disrupting the star entirely. These events are rare, and the observational evidence is still a field of active research and debate. But they are important because they expand the map. They remind us that supernova is an umbrella, and nature uses more than one method to open it. You do not need to memorize these rarities tonight. You only need to notice the scientific posture. When an event does not fit the standard power sources, we look for additional energy reservoirs, interaction, central engines, unusual progenitors. We test these hypotheses against the evidence, spectra, light curve shapes, host environments, late-time behavior. The outlier shelf is not a junk drawer. It is where new physics sometimes hides. Now, let's take a slow detour into the pre-explosion lives of stars, because the ending depends on what came before. For core collapse supernovae, the progenitor is a massive star, and its final structure depends on its mass, metallicity, rotation, and whether it has a companion. Stellar winds can strip envelopes, binary interactions can remove hydrogen or helium layers, episodic mass loss can create dense circumstellar shells. These pre-explosion processes shape what we see after collapse. In some cases, astronomers have identified progenitor stars in pre-explosion images for relatively nearby supernovae, especially red supergiants for Type 2P events. These identifications are rare and challenging, but when they happen, they provide a direct link between a living star and its explosive death. For Type 1A supernovae, the progenitor question is more elusive. White dwarfs are faint, and the binary systems involved can be hard to detect in advance. The debate over single degenerate versus double degenerate channels continues, with evidence supporting contributions from multiple pathways. Some events show signs that might be consistent with interaction with a companion or circumstellar material. Others do not. Some remnants may show hints of surviving companions. Others are ambiguous. The field continues to refine constraints through observations, modelling, and statistics. This is another way the case file stays calm. It allows for multiple channels where evidence supports them. Science does not need a single story when the universe provides multiple. It needs a framework that can incorporate variety without losing predictive power. Now, let's return to Cassiopeia A. One more time, because it offers a particular kind of lesson. The last moments before collapse may not be quiet. The idea that a silicon-rich layer pushed outward into a neon-rich layer shortly before the explosion suggests that the interior was not neatly stratified right up to the end. There may have been large-scale convection or wave-driven mixing, instabilities that stirred layers. This stirring could influence nucleosynthesis yields, explosion asymmetry, and remnant morphology. It also ties into a broader theme in core collapse modelling, the importance of multidimensional effects. In one dimension, you can write a neat story. In 3 dimensions, turbulence, convection, and instabilities make the story more complex and more realistic. When you hear unresolved problems in supernova theory, It often means the problem is inherently multidimensional and involves complex physics, neutrino transport, fluid instabilities, nuclear burning, turbulence, magnetic fields. These are hard problems, not because the universe is trying to hide, but because the universe is doing many things at once in extreme conditions. The calm part is that the evidence keeps arriving and models keep improving. The case becomes clearer over time, even if some pages remain open. Now, I want to give you a gentle way to keep track of the two main engines without getting lost in details. You can think of core collapse supernovae as events where gravity wins a long negotiation, and thermonuclear supernovae as events where nuclear burning runs away because a thermostat fails. Gravity winning versus thermostat failing. Collapse versus runaway. Both are ends, both are bright, both are rare compared to ordinary stellar life, and both leave traces we can read. If you like, you can also think in terms of what remains. In collapse, something can remain, a neutron star, perhaps a black hole. In thermonuclear disruption, the compact object may be unmade, leaving no central remnant, only expanding debris. This is not universal, but it is a helpful heuristic. Now let's take another slow pass through the spectrum evidence, because spectra are like fingerprints, and they deserve a patient look. A spectrum shows absorption and emission features corresponding to elements and ions. In supernovae, these lines are often broadened by high velocities. The ejecta is expanding at thousands to tens of thousands of kilometers per second. The expansion causes Doppler shifts, and the lines can appear as P Cygni profiles with blue shifted absorption and red shifted emission, reflecting the geometry of an expanding photosphere. The presence of hydrogen lines indicates hydrogen-rich material. Helium lines indicate helium. Silicon lines, especially a prominent feature near 6,150 angstroms in Type 1a spectra, are part of what defines normal Type 1a events. As time passes, spectra evolve. Early spectra probe outer layers, later spectra probe deeper layers as the photosphere recedes. In core collapse supernovae, you may see lines from hydrogen early, then later see lines from heavier elements as deeper layers become visible. In Type 1, a supernovae, early spectra show intermediate mass elements, later giving way to ion group features as the ejecta becomes optically thin and the inner nickel-rich regions dominate. Spectral evolution is like peeling back layers with time, not physically removing them, but changing what is visible as opacity shifts. There is a comfort in this. You do not have to cut a star open to see its structure. Time and expansion do the peeling for you, and photons carry the story. Now let's talk quietly about distances, because Type 1a supernovae have been used as cosmological rulers, and this connects supernova physics to the larger scale questions. When a Type 1a supernova is standardized, it can provide a distance estimate. When many are observed at different redshifts, they can trace how the universe's expansion has changed over time. This is where the discovery of accelerated expansion came from. Distant supernovae appeared dimmer than expected in a decelerating universe, implying that the expansion has been speeding up. This inference depends on careful corrections, calibration, and understanding of systematics like dust and evolution. It is one of the reasons large, uniform surveys are valuable. They can reduce uncertainties and improve the statistical power of the sample. Romans survey, by producing a large number of Type 1a light curves in a consistent way, is expected to tighten constraints and reduce certain systematic errors. It will also provide a rich dataset for supernova astrophysics beyond cosmology, including core collapse populations and rare transients. The same survey that helps measure the universe's expansion also helps map the diversity of stellar death. This dual utility is another quiet theme of supernova science. One phenomenon can serve as both a tool and a target. Type 1. A supernova are tools for distance, but also targets for understanding progenitors and explosion mechanisms. Core collapse supernovae are targets for understanding massive stars and nucleosynthesis, but also tools for tracing star formation and feedback in galaxies. A supernova is both a measurement and a mystery. Now let's return to feedback, because supernovae do not just enrich, they shape their environments dynamically. When a supernova explodes, it injects energy into the interstellar medium, driving shocks, heating gas, and stirring turbulence. Supernova remnants can accelerate cosmic rays. Multiple supernovae in star-forming regions can create superbubbles, carve cavities in the gas, and influence subsequent star formation by compressing or dispersing clouds. In galaxies, supernova feedback is a key ingredient in regulating star formation and shaping galactic evolution. It is one of the ways small-scale stellar processes influence large-scale structure. Again, the calm way to hold this is to imagine the office air after a window is opened briefly. A gust enters, mixes the air, shifts papers slightly, changes the distribution of warmth. The office does not become a different building, but it becomes a different atmosphere. In a galaxy, supernovae shift the atmosphere of gas and dust, stirring and heating and redistributing materials. Now let's take a gentle inventory of a few famous supernova remnants, because they serve as reference points in the case file. The Crab Nebula, tied to 1054, is a pulsar wind nebula, energized by a rapidly rotating neutron star. Tycho's and Kepler's remnants are associated with historical supernovae and have been studied to infer the type of explosion, with evidence pointing toward type 1a for Tycho, for instance, based on spectral properties of the remnant and the lack of a compact remnant. Cassiopeia A, as we've discussed, is a core collapse remnant with rich element mapping. Each remnant offers a different angle: pulsar-powered emission, shock-heated shells, element distribution, interaction with surroundings. Together, they show that the aftermath can be as diverse as the explosion itself. Now, because tonight is a sleep story anchored in hard science, I want to give you a quiet laboratory sequence that feels like handling evidence on a desk. Imagine I slide 3 photographs across the lamp's light, one by one. Each photograph is a light curve, simplified to a smooth line. The first rises steadily, reaches a peak, then declines in a smooth curve. It has a certain symmetry, a certain cleanliness. This is the type 1a archetype. It looks like a controlled burn, a compact event that is bright and then fades in a predictable way. In the details, there are variations, but the family resemblance is strong. The second rises, then settles into a broad plateau, like a long straight stretch of road at the top of a hill. This is the type 2p archetype. The plateau is the hydrogen envelope doing its regulating work, recombining and changing opacity as the ejector expands. The third rises and falls more quickly, with less of a plateau, perhaps with a sharper decline. This could represent a stripped envelope core collapse event, where the absence of a thick hydrogen coat allows faster evolution. Now imagine a fourth photograph set slightly aside because it is stranger. It rises to an extreme brightness and stays luminous for a long time, or it has an unusual shape that suggests additional power. This is the outlier shelf. Superluminous events, interaction-powered events, central engine candidates. These are not the majority, but they are part of the landscape, and surveys help us find them and understand how rare they truly are. This laboratory sequence is not just imagery. It mirrors how astronomers actually work, classify by light curve, refine with spectra, infer progenitor properties, compare to models, and build populations. Now, there is another quiet factor that shapes what we see: dust. Dust in the host galaxy can redden and dim supernova light. Correcting for dust is essential for using type 1, a supernova, as distance indicators, and it also matters for understanding core collapse populations, because dust can hide explosions in star-forming regions. Infrared observations can help, which is one reason space-based infrared surveys are powerful. Dust is a reminder that the universe is not a clear vacuum. It is filled with material that both creates stars and obscures them. In my office, dust is the soft film you only notice when the lamp hits at an angle. It does not change the existence of the objects, but it changes how clearly you see them. Astronomy is full of such films: dust, bias, selection effects that must be accounted for when reading the sky. Now, let's talk a little about time, because supernovae force us to think in multiple timescales at once. The progenitor star lives millions of years. The final burning stages can be days or hours. The collapse happens in fractions of a second. The neutrino burst lasts seconds. The shock travels outward and breaks out in minutes to hours, depending on the star's radius. The optical light curve evolves over weeks to months. The remnant expands over centuries and millennia. The elements dispersed by the explosion may take millions of years to be incorporated into new stars and planets. One event spans time like a long piece of music, from a sudden note to a lingering echo. This layered time is part of the reason supernovae make such compelling case files. They are singular events with long consequences. They are brief enough to catch in human lifetimes, yet deep enough to connect to cosmic evolution. Now, I want to return once more to the idea of inner conflict before collapse, because it helps us hold a subtle point. The progenitor's immediate pre-collapse state can influence observable outcomes. In the final stages, burning shells can drive convection, creating waves that carry energy outward. This can potentially enhance mass loss or alter the star's structure. In some supernovae, evidence suggests enhanced mass loss shortly before explosion, leading to dense circumstellar material. In others, pre-explosion outbursts have been observed in some luminous transients. The line between late-stage stellar variability and the onset of explosion can be thin. Cassiopeia A's evidence of last hour's mixing fits into this broader theme. The final approach to collapse may be dynamic and messy. Yet even this messiness can be approached calmly because it is governed by physics. Fluid instabilities, energy transport, nuclear burning rates, gravitational collapse. The star is not conflicted in an emotional sense. It is in motion because the conditions in its interior demand motion. In my office metaphor, it is the difference between a stack of papers sitting perfectly still and that same stack in a room with a slow fan. The fan does not want to move the papers. The air flows, and the papers respond. In a star, energy flows, and matter responds. Now, let's drift into the late phases of supernova study, nebular spectra, when the ejecta becomes thin, and we see emission lines from deeper, inner regions. In this phase, the supernova is no longer a photosphere with broad absorption lines. It becomes a glowing nebula with emission lines that trace element abundances and ionization states. Nebula phase observations can provide constraints on the amount of nickel synthesized, the distribution of elements, and asymmetries in the ejecta. For type 1, a supernovae nebula spectra can reveal the inner iron group elements and provide clues about explosion models. For core collapse supernovae, nebula spectra can show oxygen and other elements that trace the progenitor's core. Nebula spectra are like opening the file long after the headline has faded, finding that the most revealing pages are not the first ones, but the later ones. In some cases, the early light is dazzling and the late light is subtle. But subtle does not mean unimportant. Subtle is often where the constraints become sharp. Now, because you're listening to this for sleep, I want to offer you a simple, repeating cadence that you can return to whenever the details feel like they might drift. Mechanism, signature, inference, mechanism, collapse or runaway burning. Signature, hydrogen lines, silicon lines, plateau, decline rate, remnant, neutrinos. Inference, envelope thickness, nickel mass, progenitor channel, explosion asymmetry, distance. Mechanism, signature, inference. You can let those three words be like steps down a hallway, steady and evenly spaced. Mechanism. A massive star builds an iron core, collapses, and launches an explosion aided by neutrinos and complex multidimensional dynamics. Signature. Hydrogen in the spectrum, perhaps a plateau in the light curve, a compact remnant left behind, element-rich ejector. Inference. A red supergiant progenitor, a thick envelope, a certain range of ejector mass and energy. Mechanism. A white dwarf approaches ignition and undergoes thermonuclear runaway. Signature. No hydrogen, characteristic silicon features, a relatively uniform light curve family with a standardized relationship between decline and brightness. No obvious compact remnant. Inference. A thermonuclear explosion producing nickel, useful as a distance indicator, with ongoing debates about progenitor systems. Mechanism, signature, inference. The case stays calm. Now let's take one more extended walk through the historical record, because it can be soothing to place modern science within a long arc of human attention. In 185 CE, Chinese records describe a guest star. Over centuries, other guest stars were recorded. These observations were not made with the aim of building a supernova catalogue, but they became part of one by accident, by the simple act of noticing. When modern astronomers identify remnants and compare their ages, positions, and properties to historical reports, they create a link. That link is not always perfect. Historical coordinates can be imprecise. Records can be ambiguous. But when the match is strong, it is a beautiful continuity. A human witness, a written note, and a modern X-ray image of expanding debris. The Crab Nebula is perhaps the most famous of these links. Its pulsar ticks steadily, a lighthouse of rotation, while the nebula glows in filaments. The remnant is a system still evolving, still interacting with its environment, still accelerating particles. It is the afterlife of a moment recorded nearly 1,000 years ago. It is as if the file has remained open on the desk for centuries, accumulating new evidence with each generation of instruments. Now, back in the modern survey era, we can imagine a different kind of historical record. Not a handful of guest stars over centuries, but tens of thousands of transients over a few years, each with a measured light curve, each classified and archived. Roman's Plan Survey is one example of this shift. It is an attempt to make the transient sky systematic, to turn surprise into dataset, to catch not just the obvious, but the subtle, to provide enough volume that rare events become detectable and the distribution of common events becomes precise. When you have enough events, you can also see how environment matters. Core collapse supernovae trace star formation, so they are more common in spiral arms and irregular galaxies with active star formation. Type 1, a supernovae occur in a wider range of galaxies, including ellipticals, because white dwarfs can explode long after star formation has ceased. These demographic differences are part of the evidence too. They are population-level signatures that support different progenitor stories. Now, let's address a quiet philosophical point. Why do we care about understanding supernova mechanisms in detail beyond the aesthetics of a cosmic explosion? We care because supernova influence chemical evolution, galaxy evolution, and cosmological measurements. If type 1 supernovae are used as distance indicators, understanding their progenitors and potential evolution is essential for precision cosmology. If core collapse supernovae are key sources of elements and feedback, understanding their yields and rates influences models of galaxy formation. If supernovae produce neutrinos and gravitational waves, understanding their dynamics connects to multi-messenger astronomy. Supernovae sit at a crossroads of astrophysics, but we can keep that crossroads quiet. We do not need to stand in the traffic. We can sit on a bench near the intersection and watch the patterns: light, spectra, remnants, particles, catalogues. Each is a road leading to a different question, and the questions can be visited slowly. Now, I want to bring the office metaphor to a gentle climax, not with noise, but with clarity. Imagine the office as a star. The outer shelves are hydrogen, abundant, light, easy to move. The desk is helium and carbon, denser, closer to the work. The drawer of paper clips and metal objects is iron, heavy, settled, reluctant to change. The lamp is the core's energy generation, steady for a long time. The air circulation is convection, moving heat and material. The mug's steam is expanding ejector. The folder labelled Supernovae is the moment of transition, when the star's life becomes evidence. In a core collapse supernova, the drawer of iron becomes too heavy, the desk can no longer support it, and the whole inner arrangement collapses inward, then rebounds outward in a complex neutrino-aided surge. Papers lift slightly as if a pressure wave passed, and then settle into a new arrangement. Debris distributed across the desk and floor are new structure. In a type 1a supernova, the lamp's bulb itself becomes unstable. A runaway burn consuming the source, leaving no lamp behind, only light and warmth briefly filling the room before fading. These metaphors are not meant to replace the physics. They are meant to make the physics feel like something you can hold without strain. Now, as we near the end of this file, I want to revisit the simplest evidence one last time: the light curve. If you fall asleep holding only one concept, let it be this: brightness over time is a story, and the shape of that story is an imprint of mechanism and structure. When you see a plateau, you are seeing an envelope regulate radiation escape. When you see a smooth decline correlated with peak brightness, you may be seeing a thermonuclear family with nickel-powered fading. When you see an unusually luminous and prolonged event, you may be seeing additional power sources or rare progenitors. And when you see the late time tail, you are seeing the slow work of radioactive decay and transparency. Mechanism, signature, inference. The universe leaves traces. We read them. I'll place the supernova folder back beneath the lamp, not as a closed case, but as a case that rests for the night. There will be more data, more surveys, more refined models, more remnants mapped in exquisite detail. There will be new transients that challenge categories and force the map to update. There will be quiet improvements in catalogues, in calibration, in how we connect historical records to modern observations. The sky will keep changing, and the evidence will keep arriving. For now, the office holds steady. The lamplight pools warm across the desk. The mug's steam curls and fades. Outside the window, the dark sky remains what it mostly is: vast, patient, and full of events that do not hurry for our convenience. If a star ends tonight somewhere in that darkness, its light will travel for years, centuries, or millions of years before it reaches anyone. When it does, it will arrive as a curve and a spectrum, a set of calm numbers and lines that tell a story of collapse or runaway fire. And somewhere, in some quiet room, someone will open a folder and read it gently. Good night.